My name is Harold Cook. I'm from Lightfleet Corporation, and I'm here to talk about an approach that we're taking to overcoming the inefficiencies that we see in routable network protocols. I'm not going to go into a lot of depth. I'm not going to turn this into a tutorial on networking and packet routing. A lot of that information is available, so I'm going to assume that for the most part, everybody in the audience is generally familiar with networking and the way that packets are routed. But for the purposes of this presentation, what I want to do is I want to just define network packets as containing control information, which is, as we all know, is generally one or more headers depending upon the type of protocols that are being used, and then verification information such as checksums. And then associated with that control information is data or payloads within those packets. So I'm going to take a rather simplistic view of it. And I'm also going to mention one other thing, that throughout this presentation I'm using a couple of different graphs on performance and measurements that we've taken of some typical Ethernet switches. And the one piece of information that I'll make sure that everybody understands, when I'm talking about these measurements, what I'm doing is I'm talking about user space to user space timing. I'm not looking at traffic generators where you've got it connected directly to a switch or the network infrastructure. I'm talking about real data timing to a real user application. So associated with all of these packet headers is each switching has a tremendous amount of software that's used to examine the control information in these packets and basically determine where these packets need to go through the infrastructure from where the particular switch sets. In a lot of cases, these are software-based lookups as opposed to hardware-based lookups. And then you've got to consider that there's several different types of packets that are out there floating around the network. You've got unicast or point-to-point packets. You've got broadcast packets, which are generally, one packet to all of the ports on the switch. And then you've got a more interesting case, which is multicast, which is a packet that goes from a single point to a subset of the ports on a switch. And then a lot of this is also dependent upon how the switch is actually configured, whether it's configured for store and forward or cut through. I want to talk a little bit about the special case of multicast. Multicast packets in a routable network switch today is particularly onerous, primarily because if you think about the transition or the development of the technology that's in use today, multicast was lost when we went from bus-based topologies to star-based topologies. In the old Ethernet, on a bus-based Ethernet network, on a cable or on coax or whatever, each multicast destination would define a multicast address that it was to receive. And when you had that packet transmitted on that bus, it would go out and each one of those nodes would pick it off. And so basically you ended up with a situation where you got nearly simultaneous transmission of that packet to a number of nodes on the network. When we went to a star-based topology, silicon didn't have a really good way of replicating that on Ethernet. And so what really happens in a switch is that it goes from if you have it configured for cut-through, it switches over to store and forward. Then it retrieves a list of the ports that packet needs to be transmitted to, and it goes into a serial retransmission of those packets. And what this typically leads to is that you end up with a lot of skew and jitter in the transit times of these packets over the network. And so you end up with a lot of potential for congestion, and congestion is generally a bad thing in a routable network because you end up throwing packets on the floor. And this particular chart right here is an example of a network. It was an Ethernet network with adapters, NICs, that are generally acknowledged as being particularly high performance, with a switch, and I'm not going to publicly say who that was. If you're really curious, I can talk about it privately. But a switch that's acknowledged as being one of the higher performing Ethernet switches on the market today. And what you see in this particular situation, let's see, I think I've got a laser here, right? I do. These data points here, the destination ports are listed across the bottom here, from 1 to 22 in this particular case. These data points, the fact that these data points are all over this chart, are indicative of the jitter that you see in a packet that's being transmitted, through this store and forward type of methodology. And then the fact that this line, this least squared fit line, average arrival at these ports, has an increasing slope to the right is indicative of the fact that it's actually going through and retransmitting these packets rather than sending it all at one time. Oh, and one other point I want to make over here. This time scale over here is in microseconds, and if you look at that, I don't know how visible it is on that slide, but that's actually centered around 53.5 microseconds. When we talk about congestion, that is another situation where you run into too much data trying to work its way through a switch at any given time. Lost packets are a result of congestion. Switches will throw packets on the floor. I was actually running one particular test scenario where I was able to get this same switch to throw about 80% of the packets that I was trying to transmit on the floor just by generating too much data to try and cram through the switch. And the problem with that is that incurs additional software overhead, typically in the TCP layers, to try and recover those packets and retransmit them, which then you start a snowball cut type of situation where you're throwing data on the floor and you're trying to cram more data through the switch to recover what you've thrown on the floor. And it generally turns into a pretty ugly situation from there. So just to kind of summarize typical routable networks today, packets basically carry everything that they need in order to work their way through the network. And every switch along the way has to use whatever software is running in that switch typically to determine where that packet needs to go, which all adds to the software latency. And again, talking about multicast in particular, they're typically handled very poorly. So I want to present what essentially is a new approach to this, which we call switchless networking. And basically what it is it's enabling a protocol that allows hardware routing and basically eliminating all of the software from a switch. In other words, eliminating everything above most of layer 2. There's still some of the layer 2 types of functionality there, but everything else above that is essentially removed. And what I want you to do, just for the purposes of this presentation, is to consider a particular scenario. Many applications that are out there today, either in a cluster, typically in a clustered type of environment, are relatively static in the way that they're configured. So the question becomes, if you've got a static network configuration, then why should you pay the overhead, the performance overhead that you're incurring for a routable network to be able to route a packet outside of an environment where you're not necessarily interested in having it go, and the associated software overhead to support that type of environment? And some of the examples that I'm thinking about when I talk about this, you think about a storage network. Either the front side of that in front of like a NAS controller, or even behind that if you have a NAS controller that's sitting in front of a bunch of intelligent hosts that are managing all of the physical disks, or even NVMe fabrics. You may have a static set of NVMe hosts that are providing data services to a large cluster of machines. You might also consider multi-host applications that run for long periods of time, such as market analysis or trading tools. Billing systems. Think about a cell phone billing system where you've got a lot of data that's being generated and stored in a very static configuration or an inventory control system, or even big data analytics machines or HPC clusters. Most of those types of applications are relatively static. There's not a great need to change the configuration, and that in many clusters, changing the configuration generally means rewiring the network, which is not something that a lot of people like to do very often. So what's the alternative to all of this is basically a connection-oriented protocol where you essentially enable routing packets at hardware speed rather than having to do the software lookup in order to be able to get that. And most importantly, and one of the key points to this is that we actually enable a reliable data transmission. This network does not lose data. It does not drop packets because of the flow control hardware that we have built into it. Everything in this network is inherently multicast. And there is no skew in the endpoint arrival time. So I showed you that chart a little bit earlier where you're showing the skew and the jitter in that. And I'll show you another chart in just a minute. And unicast is essentially handled as a very simplified case of multicast. But the key is that everything is handled inherently as a multicast packet. This animation that we have running here actually shows half of a transmit-receive pair. This is actually a transmit pair from essentially an HBA, or you can think of it as a NIC replacement. This is all of the flow control logic and the determination of where that packet goes, and then out of this logic, you actually transmit those through to a FIFO where it's going to the output ports over here. So in this particular case, we've got a switch radix of 24 ports. And then this same logic would be reversed for each one of those ports. Couple all of that hardware capability with a kernel bypass architecture. And basically RDMA style transfers where it goes from user memory to user memory. And you basically, at that point, eliminate the entire driver stack. We do have device drivers that are used to manage the subscription tables that enable this hardware packet routing. And then, in addition, add on top of that standard APIs such as verbs or OFED or even a Ethernet NIC emulation so that you can use the standard TCP/IP stack. I want to talk a little bit about this connection-oriented protocol. In essence, what we're doing is we're proposing a change to the programming paradigm for a typical network type application, where what we do is we define resources on the network as a group. So for example, if you had a particular data type that needed to be transmitted to from one machine to another, or from one machine to a group of machines, you define what's essentially a group. And then any data written to that group is transferred to all members of that group simultaneously. Groups are dynamic. You can have a host join or leave a group depending upon the configuration of the application. And then by doing this, the packet routing is essentially determined by the group identifier. So at that point, you're doing a lookup of a subscription table at hardware speeds rather than having to do it through software. So you get very, very low latency and very high throughput through the switch. Again, I want to mention that everything is inherently multicast. Data is moved through the switch replacement, or a DDM. We call it a data distribution module. There is no skew and no jitter because of the hardware architecture. This becomes critically important in time-sensitive applications, and I can talk about a couple of those if anybody's curious. And again, just to mention that true multicast was lost back in the early 90s when we transitioned from bus-based Ethernet to star topologies. And quite frankly, there's a number of people out there that have done some research on multicast, and there are some very beneficial reasons for having a true multicast capability. But I think there's opportunities for more. So that chart that I showed you a little bit earlier with that Ethernet switch, this is what it looks like with this architecture. There is a little bit of jitter that you can see here among these particular data points, and that's because of the accuracy of the PTP clock that we were using. I had the clock running at somewhere between 20 and 50 nanoseconds of accuracy on this network. So the fact that there seems to be a little bit of jitter here is I attribute that more to the accuracy of the clock as opposed to actual jitter. And then you'll notice that all of this same data, this is absolutely the same application that had the capability of running over the TCP/IP stack through the Ethernet switch, as well as the API for this particular architecture. And where that other chart was centered at 53.5 nanoseconds, you'll notice that this one is centered right around 4.5. Significantly faster. Also, both of these charts were averaged over about 10 million packets. So this was not a single packet timing. It was averaged over an extended period of time.
So no drop packages or no retransmission?
There is no drop packets in this network. I have been working with this thing now for 1.5 years, and I have moved billions of packets across this network of all sizes, and I have never seen a drop packet. And that's all because of the flow control architecture. A lot like a lot of things that we've talked about here over the course of the last several days, particularly around RDMA, we have a kernel bypass architecture, so there is no kernel or network stack overhead. User applications go directly to the hardware to transmit the data. We have what is essentially zero copy data transfers. You build a buffer in the application and move data from there, and that has some interesting implications. As I mentioned, we do have some kernel drivers that are used to initialize the hardware subscription tables and manage those over the network. We're looking at industry standard APIs, as I had mentioned, OFED and verbs, and again, NVMe over Fabric. And then through some of the information that I've gotten at this conference here, I've actually got some other ideas and some other approaches that we will take potentially to this same problem. Big data analytics, whether it's Hadoop or Spark or Cassandra or any of the big data analytics types tools, actually have a network layer abstraction called Netty. And we're looking at an implementation of Netty over this so that we can actually reliably move data. In this particular environment, if you think about a map-reduce type of operation, if you're familiar with that operation, you basically move a large data set from one host to a number of hosts and then generate a search across those data sets on those remote hosts. Think about being able to move all of that data at once rather than having to move it for every host, and the types of performance improvements that you could get in this environment with this type of architecture. And then a network emulation, we actually have a Ethernet driver that sits on the bottom of the TCP/IP stack so that you can run standard TCP/IP in Linux sockets and give you essentially access to those interfaces. We've talked a lot about persistent memory at this conference. So there's several ways of thinking about persistent memory. And again, persistent memory being the byte addressable form of the non-volatile memory. You basically expand the front-side bus architecture with such things as Gen Z or some of the modifications to system architectures that other large processor suppliers are looking at. But also, when you start talking about persistent memory in terms of NVMe, having the lowest latency, highest throughput solution over a reliable network also has a lot of benefit. Again, not losing any of that data, being able to move it reliably across the network, and handle the NVMe protocol in a reliable, or NVMe over Fabric protocol in a reliable way would have particular performance benefits. So in essence, by eliminating the software from the switches and providing a hardware routing capability, you end up with a network that is much faster, simpler, and far more reliable than anything that's out there today. Questions?
So is this for a fixed number of devices? Is that how you set this up?
If you look at the technology, it's not.
Okay.
The limiting factor is the subscription table in the switch replacement. If you had a very large memory available to be able to go do that lookup, say for example 64 bits, you begin to see that you can get to an architecture that is, not to fall into Bill Gates' problem of 640K is the largest memory you'd ever need in a machine from many years ago, but 64 bits is a very large number of machines. And that's an enhancement to the protocol that we're actually looking at today. It's the ability to scale that out to a much larger capability. Sure.
Yeah, you showed us the demuxing part of the whole switch energy.
Mm-hmm.
So that's the easy one. What's the muxing part? So usually congestion comes from egress interfaces and then propagates through the network.
So that's kind of the secret that lives in that yellow box that was on that animation. There are some patents that have been filed on this technology, and if you go look at the patents, you can take a look at it and figure it out. But it's not something that I can openly talk about other than that.
Could you say if it is a TDM-based approach or a bandwidth allocation approach or something like this? It's very high level.
Well, this is where me being the software guy trying to talk about the hardware implementation is a bad thing. I don't know how to answer that question. But if you'll give me your card, I'd be happy to get you that information. Yes?
Sanity check that hosts can be part of multiple groups?
Yes. Any application can define multiple groups. In fact, if you want to have a very high-speed throughput, unicast type of connection to a number of different hosts, you just open multiple groups with different host addresses.
Great.
And then you can move data through that network very, very quickly. Any other questions? All right. Being the last person before lunch, I don't want to stand between everybody here and lunch, so thank you for your time.